Consider the following truss bar, subjected to an axial load, and these typically transfer axial forces because they're too slender to support bending loads. Now if we cut out an element of width delta x and take a horizontal equilibrium of forces, we have P of x plus delta x minus P of x is 0. And if you divide this through by delta x and take the limit as delta x goes to 0, then this is the definition of the derivative of P with respect to x, and that's 0. So this means that P is constant throughout the entire bar. And this can be seen by a horizontal equilibrium of forces. So wherever you cut this bar, the force in the bar is going to be equal in magnitude to the external load. Now if we consider the following relationships, being the stress is the force on the cross-sectional area, and the strain is equal to the displacement at the end of the bar on the undeformed length of the bar. And for linear elastic behavior, the Young's modulus is the stress on the strain. Therefore, we see that the force is equal to the stress by the cross-sectional area and we assume these are functions of x. So for example, for the general case, where the cross-sectional area of the bar is not constant. And we know that the axial strain is the first derivative of u with respect to x anywhere along that bar. And using this relationship, for a linear elastic bar, the stress is the Young's modulus by the strain. And now we can separate the variables. So we have du is p on e to the x dx. And for a bar with a constant area, the cross-sectional area is constant, so we can take these outside the integral, and therefore u of x is equal to p on ea by x plus a constant of integration. And if the bar is restrained on one end, so we have the displacement at the support is 0, so that gives the constant of integration is 0, and therefore we get rid of it. So at x equals L, u is equal to PL on AE. And as expected, this result can also be obtained from these three relationships directly. Please subscribe, like and comment to help me reach more students.